The Ukrainian AI community used to create, develop, and educate for a shining future. But then Russia ruined our peace. We switched to a new reality. We do our best to defend our country. The brightest AI minds came to share knowledge with us. Together, we will build a technological and secure future. Peace in Ukraine equals peace in the world. Support Ukraine. Support the AI community.
Hi everyone, welcome to AI for Ukraine. So for people who are based in Ukraine, I hope you guys are feeling safe and excited to join this session. So for people who are attending for the first time, a couple of words about this initiative. So AI for Ukraine is an educational project organized by AI House and aimed to connect AI experts from all over the world to support Ukrainian AI community. So thanks to everyone who joined our previous sessions. Thanks speakers for their willingness to participate in sessions. And thank you everyone for your donations. We have already collected 250,000. So congrats to everyone. It's a huge achievement. So money are gonna go to one of the biggest foundations, Come Back Alive. And my name is Yulia. I'm product marketing director at DataRobot. My superpower, I'm Ukrainian, and I've been in the industry for 8 years. And I know, practically speaking, how I can shape the future of many industries. So we are here today to learn more new things, amplify our knowledge in our current or future projects. And today's sessions will be with Alex Smola about automated machine learning with Autoglon. But before we get started, I want just to emphasize that for session, during the session, you can ask questions and you can use Slido for that. You can access through QR code, or you can open in the browser and put AI for Ukraine code. You can vote questions, so please do not hesitate, ask questions during the session. And we'll have time to get responses from Alex. And if you're new to Slider, I recommend let's take a quick test together. We'll have a short poll. Yeah. So quick test round. Have you guys watched the previous session? Okay, so I'm seeing there are some new folks here, definitely. That's actually pretty cool to see that there are some people who enjoyed the session, and there are new people as well. So again, ask questions, upvote for existing interesting questions, and also you have a chance to donate. Again, as I mentioned, huge accomplishment. We already collected 250,000 that will go to a foundation, Come Back Alive. And I'm happy introduce you to Alex. So a couple of words. So first of all, he's an amazing person. Second, he's a huge fan of AI and expert. So he's VP of machine learning and data science at AWS. He did a huge contribution to the academic world as well, around 500 research papers. So you definitely can learn a lot from Alex today. And lastly, I want to actually emphasize that Alex was one of the first people who supported this project and who expressed a huge interest to collaborate with us. Yeah, so Thank you, Alex, for joining us today, and the floor is yours.
Okay, so many thanks for having me here. Uh, I don't know whether you can already see me and whether we are live. Um, so I figured that probably the thing to talk about is how to solve machine learning problems quickly, because I would imagine that you probably have a couple of detection, classification, tracking, and related problems, and probably you have more machine learning problems than you have people who can necessarily immediately have the time to get a PhD in machine learning and then use it, but you might want to use it right away. But I know I'm one day late, but basically happy birthday or happy Independence Day or whatever you might say. I know one day late is usually not what you're supposed to do, but the talk is today because I was told that there are no talks on Independence Day, at least no machine learning talks. So there we are. Now, let's look briefly at, where this entire thing started. And so the guy on the photo, that's Andy Jassy. That's the Amazon CEO. At the time, he was the AWS CEO. Now he's in charge of all of Amazon. But basically, and Amazon is a large company, but nonetheless, 55,000 new tech hires in 22. I mean, at least that was the stated goal in 21. I don't know whether we made the goal. Is quite substantial. And it's really substantial if you think about it, that, this is over 1/6 of the current number of employees. So Amazon is big, but nonetheless, even then, growing by 1/6 and hiring, a medium-sized town's worth of people in as tech employees. So I'm not talking about the people carrying the boxes, and there are a lot more, but just for tech, that just tells you that this is something that actually affects the market, right? And this is a real problem if you think about it, that North America produces around 400 AI PhDs per year. So that's the United States and Canada combined. Joshua Benjo in Montreal definitely contributes quite heavily to that number, but nonetheless, I mean, it's only 400. And even if, 2/3 of all PhDs join industry, and then you can argue, well, maybe 30,000 CS undergrads. If you look at all of STEM, maybe you end up with 65 or 60,000. But it's basically a number that is comparably small relative to just the number of people that Amazon is trying to hire. Now, Amazon is not an outlier there. I mean, you take pretty much any major tech firm, you combine all of that, and the number of hires easily would be an order of magnitude higher, even just in North America. And then if you make that worldwide, it's very, very clear that there's a huge demand and not enough supply. And at the same time, machine learning competency is now really becoming a key technique for all the engineers. So not just if you have a PhD in machine learning, but just if you do something with computers, you should probably know machine learning. And so the question is, how do we get there? And one way to get there is to train a lot of people. And as a matter of fact, that's one of my responsibilities in Amazon. I run something called Machine Learning University, where our goal is to train those 275,000 people in machine learning. And, well, we make progress and it's okay, but, it takes time. So if we cannot fix the supply, maybe we can do something about the demand. And here's a short history of easy algorithms. And this is all from personal experience. So in 2010 to 2012, coding up a large linear model was PhD level homework. And this is also really where things were at, even for large computational advertising companies. let's say if you took Google or Criteo or Yahoo or others, this was the very backbone of a lot of their machine learning tools, a very large linear model on a tremendous number of features. And if you were able to code this up well, this was definitely PhD level work, and you would get promoted quite quickly and effectively. More data points there. In 2012, when I taught a large-scale machine learning course at UC Berkeley, this was probably the hardest homework to code up a large linear model. Right? Stochastic gradient descent, they struggled. Now, around 2015 to 17, by now implementing a computer vision network, well, you can do that as part of a PhD course. So 10701 at CMU, for instance, by now would typically have you implement an image classifier and do so with fairly high accuracy. And that's no longer the big boss of all the homeworks, but it's like, okay, you do that. Now, in 2021, using AutoML and a minimal amount of Python, so really like 3 lines of code, you can probably implement a very high quality image classifier or text classifier, and building a Q&A NLP system, you can probably do if you're really talented undergrad. Muli and I taught a course last year at Stanford, and this was for undergrads, and some of the undergrads are really super talented, right? But to just prove that point, so there are 3 lines of code, and I was first thinking of, should I offer some practical sessions? But hey, everybody can just, cut and paste 3 lines of code, or go to the autoglue on documentation and cut and paste it from there. We probably don't need a practical session. It's so easy. This will give you a fully fledged predictor. And well, I performed some human experiments, namely on my 16-year-old son. So he had to do some project where he needed to do time series regression. And I threw him into the deep end, and I basically told him, okay, well, just install the package, use the data, and run it. And he did, and he actually got some workable results out of it. Could he have done a better job? Of course, yes. But hey, he's 16 years old. He goes to high school, right? Just think back about what you were doing when you were 16. Probably not building a linear a non-parametric regressor. At least I definitely wasn't. Okay. So what I'm trying to say is that the barrier to entry to do something very sophisticated by now has decreased significantly. And this matters because we really want to get machine learning out into everybody's hands. I mean, it's a little bit like, well, when was the last time you implemented quicksort? Well, maybe when you took a class on algorithms and the professor forced you to do so, but short of that, that will be probably the last time you implemented it, because probably the system implementation is faster. Okay. So this gets us back to, well, what do machine learning users really want? And I would argue what they want is they want solutions, right? And okay, this is a very particular choice of cars that, I guess sell on Craigslist. But, they want solutions, not necessarily the shiniest, but, something that does the job. But then if you look at what the machine learning community is offering, it offers a lot of components. Those components are awesome. So for instance, you install Conda, then you install PyTorch, then maybe you go to Hugging Face, you git clone their repo, then you install the API keys from there, then you get maybe one of their foundation models, and then you look through the documentation and so on and so on. And yeah, you can build this. And the machine learning community is really good at building components. But what I would argue that the machine learning users really want is they want something that's automatic, where they don't have to actually think and worry about the details, and the details are automatic. I would recommend against falling asleep when using your AutoML tool, but at least it should be in a situation where you only need to interact if something goes wrong. Okay. So before I go into details, I need to ask a favor. And by the way, I just see in the messages that Bodan already asked a question, and I really want to thank him for that. Do we need to standardize the CSV files in a specific format? Well, it depends on what kind of inputs you have. So for instance, if you have mixed with images and maybe text and then other categorical attributes. So there's a description as to, what you need for the system to find where the images are. But if you want to have another data loader, well, you can do that too. So, but it's reasonably smart in detecting what the data types are. So for instance, it automatically even detects, whether you're dealing with a classification or regression problem. If you tell it, which column the label is. So we try to make it as intelligent and automatic, but I'm fairly sure you can break it. But then, really, go and you can mess with the data loader, or you can just feed it, tabular data or whatever straight away. And by the way, Bodan has done, and I hope I'm not butchering his name too much, and I'm not going to try to pronounce his last name because I'll do a terrible job. But basically, I really need to rely on your help. And I need to rely on your help by asking me questions. And the types of questions that you ask me tell me which things you're A, more interested in, but also B, the things that maybe you struggle to understand. Right? Okay, Vit is asking a fun, snarky question. Why do we need to continue implementing things in lead code? Well, it's the same thing as why I might ask somebody interviewing for a job to describe to me how a transformer works, right? If I'm hiring a car mechanic, there might not be so many times that you completely rebuild an engine. You want to make sure that the car mechanic that you're hiring knows what the various components in the engine are, such that if at some point an engine breaks and you need to rebuild it, they can do it. Okay. So understanding how the machine works is different from using the machine. Making the machine more usable is to increase the user base. And if you're interviewing and somebody wants you to show off your quicksort techniques, that means that you're interviewing for a job where you're expected to build things at the level of complexity of a quicksort and beyond. Okay. Thanks. I really like the fact that you're asking questions. This is good. This tells me that you're not asleep, and also where you stop. Anyway, so modern times. Where are we with AutoML? And this is basically the outline of what we're going to cover today. And so let's start with something from 2020. So this is when we started with AutoGluon, and well, we ran on some 39 data sets, and we did fairly well. So we failed less frequently, but still we failed once. And in 23 out of those 39 cases, we performed better than the very best of all alternatives. So in other words, you were better off just using AutoGluon than even with the benefit of hindsight combining anything else. And yeah, so this was the case for some AutoML data sets. That was the case for some Kaggle data sets. By now, our benchmarks have gotten bigger. But nonetheless, we failed once, and we fixed that since. And I'll tell you in a moment why AutoGluon is so insanely robust. So here's where we are by now. This is from Peter Geisbers. As part of his PhD thesis, he compared a number of AutoML systems. I think the entire thesis started out by trying to build a new one that was better, and ended up being a very thorough benchmark. And really, really big hats off to him, A, for sharing this early, B, for just being very honest and just saying, okay, let's just compare what's there. And yeah, we do not too poorly. And basically, what you want, this is essentially the rank. And this is basically, if you were to look at, every data set as a competition and a contest, and, where do you place from rank 1 to rank 10? There are 10 systems that he compared. And I mean, it's unlikely that you always win, but think of it a little bit similar to Formula One, where even if you don't win every race, you can still win the championship. And that's kind of what's happening there. Details don't matter, but basically, it's pretty good. Now, onto the failures. So out of 2,080 data sets, we failed exactly 3 times. And those 3 failures were out-of-memory failures. So they could have easily been fixed by, just running on a larger instance. But in any case, we do pretty well. So yeah, I don't think I need to go into like a crazy amount of detail there. This is basically different classification and regression problems. And 2 things to maybe call out. One are the relatively small error bars in the sense of, scale performance. And if this bar is large, it means that, sometimes the system works really well and sometimes it works spectacularly, awfully poorly, right? You don't want such a system which, occasionally may disappoint you really greatly, right? So you actually prefer a system that has reasonably well-defined error bars so that, no matter the situation, you always do quite well. The other thing is there are benchmarks for different allotted amounts of time. So this will come back later. And the point is basically you would want your system to get more accurate as you give it more time. And I'll get a little bit more into this later. But basically what I'm trying to tell you is it's a very reliable system and it very rarely fails. And those 3 failures could have easily been fixed by just throwing a little bit more memory at it. And I'll walk you through why it's so hard to kill autogluon with a very malformed data set, right? And that's not because we are much better engineers. Now, one thing that probably is interesting is if you look at, how we've improved over time. And so if you look at the green dot, blue and green dots on the top, so the top is basically accuracy or, normalized accuracy, because there's a lot of different data sets and you basically compare to, what's the best result you can get. And what you can first of all see is that over time, autogluon has gotten a lot faster. So the x-axis is prediction speed per row in seconds. It's on a log scale. And what you can see is that from version 0.1, which was early 2020, to now, we've gotten about 100 times faster at the same level of accuracy. So that's an okay speed up. If you're just aiming for the absolute best level of accuracy, well, we've gotten quite a bit better too. And this is compared to all the other contenders that are out there. And basically, the gap between autogluon best accuracy and the autogluon at high accuracy is as high as between autogluon high accuracy in the next best AutoML framework. So it's fairly effective, and we didn't do those experiments there again from Peter Geisber's PhD thesis, and I did not co-advise him. He did that completely on his own. He did a really good job doing very, very thorough comparisons. Okay, so that's why I actually ripped out our own benchmarks and replaced them with this because, well, yeah. Artem is asking, what's under the hood? Yes, this is exactly what we'll get to in a moment. Now, how do you compare the benchmark with custom-built models created by ML engineers? So Bodan's asking, and this is exactly the next slide. You're following straight along. Thank you. So we basically wanted to find out, how well do we perform compared to engineers? And I can tell you one quick anecdote. And the quick anecdote is, so as I said, I run this machine learning university program inside Amazon. And at the end of the time, machine learning, the engineers who were not machine learners before, but they take a course of anything between 6 to 10 weeks. It's like maybe 2 to 4 hours a week, but basically it's work. And in the end, they need to solve a problem and they need to do reasonably well to pass. And so they needed to upload their solutions. And basically, out of the 800 or 900 engineers that uploaded in this batch, so we ran AutoML and we used 2-3 lines of code. And we got within the top 3. Now you might say, well, maybe Alex, your machine learning course is garbage. Or maybe Amazon hires only idiots. Well, I hope that we don't. At least Amazon tries not to. But what this tells you is that, you could also say, well, maybe the engineers were just lazy. Well, they weren't, because they were told that they had to submit a good result in order to pass. Basically, what this tells me is that, at least compared to a non-expert, we do amazingly well. So you might ask, well, how well do we do compared to experts? And so we looked at, for instance, on Kaggle, the auto competition. And what you can do is we looked at the top 10 teams, as in the 10 teams that uploaded the best solutions in the end, and we looked at their progress over time. So this is one of the awesome things about Kaggle, that you can track this. And you can see how over a period of 1.5 months or so, they got better. And they're all approaching this 0.4 leaderboard score. And so, at some point they all exceeded. So what we did is we looked at, how well does AutoGluon do? And within 4 hours, and this is AutoGluon 0.4, so the 0.5, 0.1 is maybe a little bit better, but it's mostly faster, gets you there within 4 hours. And the best human team took 2 months to beat that benchmark. Why do I know that? Because we basically uploaded our 3 lines default config after the competition finished. You could say, well, Alex, you cheated. Well, you can look at the reference code, and it's really pretty vanilla. So what this should tell you is that now, rather than starting off at some abominable 0.55 or 0.5 score and clawing your way down to good accuracy, you start with high accuracy. And the good thing is it's batteries included but removable, so you can improve it on your own. That's okay. You can add custom models. You can do a lot of other things, right? Now, you might say, well, Alex, you cherry-picked this. Well, yeah, okay, I cherry-picked a little bit, but on other competitions, we don't do too poorly either. There's another Kaggle competition ongoing right now, again, where a default line of a few lines of code gets you to very high accuracy. So this is really it. We didn't tweak a thing. Okay. So, and by the way, Vit is asking about, interpretability and explainability. We'll get to that towards the end of this talk. And there's still a little bit of work, actually a lot of work to be done. And we'll get to how we get to the accuracy. So thanks for asking those questions. This is really awesome. Thank you. I really love it that you guys are engaged. Okay, so let's look a little bit of what goes into it. In the 0.1 release, so this was March last year. Basically, so this was 70% win rate relative to prior releases. So we have CI running, and whenever we upload and release new things, we make sure it improves. So just that very simple thing that we run CI, not just on code accuracy, but also on performance, really helps you make it go better. And so in point 1, we added, text support. We added the fast AI, tabular neural networks, and we added XGBoost, and all of that gave us a significant improvement. Point 2 got a little bit more accurate and a lot faster. And thanks to NVIDIA, so they added rapid support for GPUs. And so now, if you had a GPU, it was a lot faster. Point 3, again, bit better. A lot faster online inference because people complained that it was too slow for online. We started adding image support, PyTorch TIM, and also custom model support. And custom model support sounds innocuous, but it's a big one because usually when somebody comes to you and says, hey, can you help us solve a problem, they may already have an implementation. And usually when they approach you and they say, well, they already have an implementation, those people aren't stupid, right? So you shouldn't just tell them, well, throw away everything that you've done. I'm going to just replace you by 3 lines of Python code. Very few teams will be happy to be told that they're now useless. However, what you can do is you can incorporate their strengths by telling them, hey, look, you already built the model. Let's include that as a custom model in the rest of the RTML system. And in doing so, you will almost always get a slight improvement in accuracy, and you get a massive improvement in the buy-in of the team that you're approaching. Because now their solution is part of the new solution, right? Rather than they're now useless. So they feel a lot better, and they will be a lot more happy to adopt and use what you're doing. Okay. Point 4, quite a big improvement in win rate, and especially a very high improvement in win rate on large data sets. And that had a lot to do with much faster training speed, because if you have much faster training speed, you can try and test out a lot more options. And then, yeah. By the way, Vera is asking, do we use AutoGluon in real projects? Yes, we do. And there are a few hundred projects in Amazon that use AutoGluon in their code base. And that's about as much as I can talk about it. Okay, so point 4, we basically got Hugging Face integration done because Hugging Face has this amazing zoo of models, so why would you not? Then AutoGluon 5.1, time series support. Right now, our time series support is mediocre at best, but that was just because we needed to get something in first. Right now, it is not as good as Gluon TS just yet. Expect good things to happen with the 0.6 and 0.7 releases over time. It just takes some time until Chandler has all of that implemented. Significant improvements in fine-tuning for multimodal. So basically, if you have a big foundation model that somebody else spent millions of dollars to build, well, you want to tune it. And if you have, let's say a small model with maybe 1 or 2 billion parameters, maybe you can afford a GPU like an RTX 3090, but you probably can't afford, a computer that costs $100,000. Then you might want to be able to tune it on just the GPU under your desk. And by now you can do that. A lot more data augmentation was added. Transformers, of course, are happening. And now we can also deal with even larger data sets. 100 gigabytes isn't much yet, but it's a lot more than before, and a lot more examples. So basically, this is where we are by now. And it's an open source project, so the doors are very open. Okay. By the way, Bodan, I disagree with you on the illustrators for after stable diffusion. Look at what Randall Lewis is doing, so the guy from XKCD, when he played with DALI, and you'll agree with me that you still need illustrators. Anyway, look at his tweets. Anyway, so are we there yet? Well, actually, not really, because we still need a lot of work. And in order to get there, let me walk you through the pieces that go into AutoGluon, and then you'll see immediately all the places where we are currently still quite efficient. I mean, we are really only getting started. Okay. So after all this advertising, let me give you some very few basics on machine learning. If you're familiar with the basics, then I can walk through that very quickly. But just to make sure we talk about the same things, regression. Well, you have some data, and you want to regress some y from x, and then you just model something like y is f of x plus epsilon. And for instance, you can do quantile regression, like what's the error bars in between. What's, let's say, the between 10% and 90% range, and you want to make sure it's well calibrated. Or if you classify, so this is a binary classification problem. In this case, I picked a logistic regression function. If you have bears on one side and you have cats on the other side, you want to make sure you build some classifier such that if a different bear occurs, well, you can also classify it as a bear. And this is binary classification. This is for multi-class. This is probably one of the most famous classification data sets by now. So yeah, basically, you can see that over time, the accuracy has improved quite dramatically. So if you compare to 2010, where some teams got almost everything wrong, you might wonder, how's that possible? Well, if you have 1,000 classes, chance level is 0.001% accuracy. So it's not as crazy as it seems. But, that's the classification problem. Again, you want to solve it with AutoML. You also have object detection and segmentation problems. Again, you want to do that well. Mask RCNN being one of those. Maybe this is a generative model, and by now you can get much prettier faces, but this is, state of the art 4 years ago. Analogies. So like what man to woman is king to queen. Machine translation, text synthesis. And this is something that I just piped into GPT-J 6b. And, this is what it expanded. So I'll just read it out because it's kind of funny. So I typed, automatic machine learning is a great tool for solving estimation problems without the need to obtain a PhD in statistics or computer science. But now everybody can solve classification regression problems easily. And now this GPT-J 6b added, however, the availability of data is still one of the biggest problems of machine learning. That's actually true. This tutorial is going to show you how to use an online service for finding the next best data set for your problem. Well, that's not true. I will teach you about AutoGluon. The service is called MadLibs, and it has already a lot of data sets for your use. Well, anyway. So you can see at some point it gets a little bit deranged, but it's not too bad. This is one of the more advanced things, so visual dialogue, where you have images and text prompts. And for that, you need a pretty good foundation model, and you really should read the DeepMind Flamingo paper. It's a really good read. It's very well written. In any case, this gives you a bit of an idea of, how broad things are. So does AutoGluon support pipeline parallelism? Okay. These are the experts talking. Well, eventually we'll get there. So this gets more in the direction of large foundation model training, which isn't exactly what AutoGluon set out to do. Basically, we set out to take, let's say, pre-trained foundation models and then to, for instance, fine-tune them, incorporate them. Will we eventually need that kind of parallelism? Probably yes, if we want to do fine-tuning on much larger data sets. And by the way, Dimitra, I'm probably mispronouncing your name, but if that's something that interests you, well, we want your help. And yeah, that was a yellow and blue, and I hope I get the order of the colors right, Lego brick before with a bear. So I guess that's a cartoon that everybody's seen by now. So now let's look under the hood, because so far I just did all the advertising of, how great it is. Well, let's actually see how we get it done. So let's start with something very, very simple, namely bagging. And so, okay, what's k-fold cross-validation, right? So k-fold cross-validation is something where you just go and take all the data, you split it up, in this case, like into 5 folds, you hold out one of the folds, and you have the rest for training. And then you use the validation set to find out, how well you're doing. And so you do that for every one of the folds, and you get some numbers. And so, for instance, you might use that to adjust your learning rate in Atom, or how many layers your transformer should have, or God knows what. And you can use it to get some error estimates, like, well, how well will this work at detecting bears, or just overall tune the model of, should I add another layer in my transformer? And the thing is, once you've done this and okay, your model's good, what do you do next? And the typical answer, and I'm guilty of the same crime, is this is the thing that everybody teaches at university, and I'm definitely guilty of that crime, is like, okay, now that you know how many layers your transformers need, okay, fine, throw everything away and retrain on the full data set. And the tiny little problem is, well, does the new code actually still work? Because now it's like running CI on your code and then deciding, okay, now I know what I need to do. I make some changes to the code, and then I ship it without running CI again, right? It's the software engineering equivalent of that. And that's, of course, terrible, right? And so the alternative is to say, well, I've already done all this work. Let's actually reuse it. So here's how you reuse it. So, for instance, what you can do is you can take each of the models that you've built on one of the folds. So you have, 5 folds. And each of those folds gives me a model. And then at test time on new unseen data, I take the estimates from all the folds and I aggregate it. And in doing so, I can actually, get estimates that are much, much more reliable, because now it's a combination of multiple numbers. I get a much better idea about the certainty of the model. It reduces the variance, and it also increases reliability. So this is the one thing that a lot of people overlook. Suppose I run, 5-fold cross-validation, and maybe I'm a really awful coder, or maybe the library that I am told to use is really awful and it fails many times. In order for this bagging process to not fail spectacularly, all I need to make sure is that 1 out of 5 folds succeeds. So now, rather than needing code that has, perfect, accuracy, I just need code that fails less than 80%. Okay, I know the nitpickers might say, well, independent random variables and all of that, so I'm winging it here, right? So I guess you understand what I mean. But basically, I've just turned the situation from one where I need code that is highly accurate to one where it only mostly needs to be accurate, or at least occasionally needs to work. Because if only just 1 fold succeeds, I will have a model that at least will produce output. Will this output be great? Not necessarily, but it's much better than outputting nothing. Okay. By the way, you might then say, well, what about, large foundation models? Well, yeah, that doesn't work so nicely anymore, because if you take convex combinations of models that have, a few billion parameters each, this stuff gets really big really quickly. But it turns out there's also good theoretical reason for it. So Andrew Wilson did some cool work on stochastic weight averaging, and then there's a more recent paper on model soups, which does more or less the same thing. Turns out you can actually average in parameter space and still get something good. And yeah, we use that, and it works quite well. Okay. Dimitri is asking, how does AutoGluon fit into the SageMaker ecosystem? So first of all, we do offer AutoGluon as one of the machine learning containers that you can use in SageMaker. So if you want to use AutoGluon in SageMaker, you can. Beyond that, AutoGluon is also useful behind the scenes for a couple of other problems. Now, at the same time, SageMaker is a tool to run Jupyter in an enterprise setting with all the right security permissions and constraints and provisioning and being able to sign EDP deals and a lot of other things that I guess if you are a big corporation, you need. So SageMaker has a lot of other benefits beyond doing, specific machine learning options. But yeah, they work together and, they use our tools and sometimes they use them and sometimes they use other tools. And yeah, we do use AutoGluon in real products. Okay, so now that we've talked about bagging, let's talk about assembling. And the first time I came across assembling was in the context of the Netflix contest. And I saw, the Belcore solution, and I was so frustrated. At the time, I had a small team in Australia, and we thought, well, should we do something? Should we not? And in any case, our stuff wasn't as good. But we tried to find, the one best good model, the, principled, clean mathematical, I can prove a theorem, convergence results, and all of that model where you can accurately characterize the function space and so on. And yeah, people, including me, spent decades on doing that kind of stuff, right? So guilty of that crime, so I'm allowed to complain about myself. Now, in any case, what turned out to be the case for the Belcore solution is they just took, a combination of a couple of models, some of them prettier than others. And let's just put that into context. So if I take K and N, so K nearest neighbors, it's probably about the simplest algorithm, and you can explain it to, well, an elementary school kid, right? You tell them, hey, if the friend that stands closest to you likes bananas, then you also like bananas. Okay, or eat whatever the friend nearest to you eats, right? That's a nearest neighbor classifier. Okay, it's very robust, non-parametric, and there are really good statistical papers on it. And occasionally, it embarrasses others. So, you shouldn't be embarrassed by coming up with a solution that then gets beaten by nearest neighbors. And every once in a while that happens, and that's a very memorable lesson for whoever does that. By the way, the same thing can happen with trees, and again, they are non-parametric and robust, and then there are proofs for forests, and again, they are non-parametric and robust, and, gradient-boosted decision trees are super resilient. Or then by now, people have used deep networks, and here's, something from, basically end of 2021. By now, of course, transformers are a really good thing. And people are starting to figure out how to use transformers also for tabular data. Every once in a while, there's a paper on how to do this better. And as soon as the paper comes out, we read it. We look at the implementation. We benchmark it against what we have. And if it's better, we just grab it. So this already gets you a little bit to the point of finding the single best model. And this also gets a little bit to the issue of, why would I want to get the single best model? Well, one thing is, it's simple. Well, except that, if you look at that Frankenstein monster to the left, I wouldn't call this simple. It's a deep network, and you can say it's interpretable insofar as, hey, I've implemented a deep network, but it's not really simple in the sense that, okay, tell me what neuron 52 on layer 23 does. Well, I don't know, and probably you don't either. And the good thing is there's lots of hyperparameter tuning out there, and everybody does this. And we don't. Because the thing is, if, the model at hand doesn't fit the data, then you're kind of screwed. So you would be much better off just taking a lot of different things. And the column to the right is a small subset of all the things that go into AutoGluon. So we have like 3 different gradient boosted models because, well, 3 is better than 2, right? We have different custom tabular neural networks. We have Walpole Wabbit because, well, why not? Somebody wanted it. We have various things from sklearn whenever it's fast enough. We have things from Rapids, and Rapids tries to implement a whole bunch of things from sklearn, but the results are a little bit different. So that's why CPU and GPU results sometimes may be slightly different. Now, the thing is, everybody talks about foundation models now, and of course, well, we'd be stupid not to use them. So we grab things from Tim, we grab things from Hugging Face, and as said, if you have your own model, well, we take that too. And the reason why that combination, so you just take, convex combinations of those models, why this works is because each model has its own strengths and weaknesses. And in particular, by combining multiple different weaknesses or strengths, they have fewer weaknesses overall, which is exactly what you want. Okay, so what do? We stack things. And here's a simple description of what happens, right? So you take your input, you train a bunch of models on it, and sometimes, when you do this, you might know, this my model is generally fine, but on that kind of data, it's not so good, right? And on that kind of data, you should probably use such and such a model, right? Now, this is you as the experimenter. Well, if you can tell that, well, maybe we can do that automatically. So what we do is we just take the outputs of all the models. Together with the original input, we concatenate that into, one big fat feature vector. And then we train the same models again on now enriched features. And then we weigh things and we output stuff. And so you might worry that, isn't that training on the labels? Well, it actually turns out, and I'll get to that in a moment, that there are a couple of nice statistical tricks to prevent it from training on the labels. And essentially the same, cross-validation trick where you leave a validation fold out also allows you then to output predictions exactly in a way that doesn't depend on the labels on that chunk. And yeah, I'll get to that in a moment. But for now, essentially, this entire thing looks like DenseNet. So the first layer just generates some output, xi and then f of xi. And then the second layer, would, concatenate the outputs and then the outputs of the outputs. Turns out if you overdo this, at some point you do get label leakage. So that's why by now we're sticking to 2 layers. So 3-layer stacking does not always produce better results. And we found that it's better to spend our fixed compute budget on 2 layers and exploring more things there. In any case, so if you've ever read the DenseNet paper, this looks like DenseNet, just that we do something that looks like a Frankenstein monster, because rather than just taking, pure clean deep networks, convnets preferably, we take a nearest neighbor classifier together with boosting, together with, if you want to have a genetic algorithm, fine, we can throw it in too. I wouldn't recommend it, but you could. And so you basically get this very complex combination of models. So Artem is asking about model interpretability. And I agree that whatever comes out of this is awful in this regard. It sucks. And so can we do better? And yes, you can. And I'll get to that shortly. But let's just quickly look at, what happens here. So if you have, all the data and you produce, an estimate on, some data that you haven't trained on because it was in the validation set, then your predictions on that validation set are conditionally independent of the labels on that validation set, conditioned on the covariates, obviously. And that's really all you need in order for this to be useful features for the next round. So as said, well, you get a slight amount of label leakage for deep stackers. So you might not want to do that. Okay. Now the question is, I've walked you through a lot of basic tools for autoglue on tabular, and yeah, we'll get to that in a moment. Does it help? So the first thing you want to do is you want to look at, does more time actually lead to better models? And there's a good question, namely, is the number of models used a hyperparameter? Well, technically, it's a hyperparameter, namely, it's the amount of time that we allocate to train, right? So if you say, well, give me the best model in an hour, I get a different result from give me the best model I can get in 12 hours. And we use, the given amount of time in such a way as to get the highest accuracy model, right? And so that just means that we, train the, quick models first, and we partition our time over different levels of the stacker. And so models that are really slow to implement or, slow to run on different hardware, well, we run them last. So in that sense, we also make sure that we stay very accurately within the compute budget. So this table is about 2 years stale. So it could be that the other algorithms have improved. I can confirm that GCP tables has not. But because we ran more recent comparisons there, but basically what turns out to be the case is that AutoGluon is the only system that, most reliably improves if you throw more time at it. And that, by the way, should explain why the 0.4 release got so much better for large data sets, because then we could just actually use more time, build more models. And so whenever we replace the base learner by a fast implementation of it, it boosts our own accuracy because we can try out more stuff. Now, do the various tricks help? Yes. So for instance, oversampling and bagging is a big one. Stacking is a big one. HPO doesn't actually really help you that so much. We just use really good defaults. We tune the defaults overall, but then we don't really go and perform HPO on a per data set. Deep learning, if you take it out, it hurts a lot, but using only deep networks doesn't really help you very much, right? Now, regarding ANN indexing, so Dmitry is asking this question, and I really love it that you guys are asking questions. Are there any out-of-the-box HPO tools that can find the most appropriate library? Not necessarily. I would say Gina is probably a pretty good wrapper around a lot of those things. So Gina.ai, I think it's a startup out of Berlin. You should check them out. It's open source what they have. Yeah, that might actually be a good starting point if you want to compare a lot of different nearest neighbor tools. Okay, so by the way, the other thing that obviously you do care about is at, test time, how fast does it run? And initially when we built it and we went to some of our internal teams inside Amazon and we asked them, do you want to use AutoGluon? And they said, well, it's great, but it's too slow. And that just happened too many times. So we decided to make this one of the tunable parameters in the implementation. And so what we did, and there are really two parameters. One is namely infer limit, namely online inference latency for a single observation. And then there is one with a constraint on the batch size. And so what we now do is we automatically adapt training and ensembling strategies to satisfy this constraint. So basically, if the constraints are really tight, then you cannot, go too deeply in that. And if the constraints are really tight, well, then you cannot actually ensemble over too many functions, so you lose some accuracy, but it goes faster. And just to give you an idea about this, again, that's from Peter Geisbers. So this is looking at speed versus accuracy, and this is for different, parameter settings in AutoGluon, and you can see, the tighter you set this, the faster it gets, but also the worse it gets. And there's, with the exception of Flannel, which has one point on that curve where, okay, we don't cover that point, but short of that, I mean, we are superior to everybody else. Now you might ask, why Flannel? Well, they actually, I think, got some good inspiration from us in some aspects. Okay, so yeah, this is us. There's also one other exception, namely Teapot, and Teapot is extremely fast, but I would not recommend it in terms of accuracy. Now, how well do we compare to, signal models? Again, quite well. And I think the curve as a Pareto frontier there is a little bit misleading insofar as it really would be a convex hull, because you can always take that. But that's again misleading because the x-axis is on the log scale, so you would actually have to expand it on the full scale and then take the convex hull. And that would give you an accurate curve of what you would get. So basically, you'd draw a log curve as the convex hull if you wanted to. Okay, this covers pretty much everything about tabular data. So if you have any other questions, type them into Slido. Maybe if somebody else than the usual suspects can also ask a question, that would be awesome. Because we're going to go to multimodal data now, and this is going to get us much closer to foundation models and all the other stuff. Okay. Any questions? Okay. Is the number of models used a hyperparameter, or is it determined automatically? Well, it's determined by the amount of time, but you could disable specific models if you didn't want them. What were the biggest problems during developing the logic? I don't think there was like one single biggest problem. We have CI, we keep on adding new models as we go along. And essentially, this is, one step after the other as it improves, right? So I think probably the most striking example of that would be a post from Google Brain from a couple of years ago, where they plotted the accuracy on ImageNet for their computer vision models. And you might think of, science progressing in those, quantized chunks. And then you compare it to the curve, and it's pretty much a continuous curve. And every once in a while you have a little jump, and then you get, segments where they go and write up a paper. So what you really have is it's many, many tiny steps rather than, one drastic improvement that makes a difference like no other. I mean, that might happen every couple of years that you get lucky and somebody really figures it out, but it's really a lot of steps and a lot of persistence and just having an awesome team working on it. And the other thing is stability is really highest priority for us. So we're not going to compromise that for maybe occasionally slightly higher accuracy, because we have plenty of teams using that in production, and we don't want to, screw them over. Okay. So, if there are no more questions, let me Oh, Vit asked, is AutoGluon part of SageMaker Autopilot? The answer is no. And I'll leave it at that. And you can draw your own conclusions why, and you can ask yourself also why. And I think that's all I can say about that question. Okay. So here's a Kaggle competition data set, and there's a cat, and I think it's probably one of the uglier cats they had in there. Maybe they're just bad at taking photos, or maybe the cat is just malnourished. In any case, there's a text description of that poor cat to the lower left, and then there are some features, and basically the question is, will somebody adopt the poor cat? Right. And by the way, this might be the record where, the images are in Varlib, Jenkins, workspace, AutoGluon, da, 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 da. So this is, the type of record that you would want. So basically, the image should have, the file path to the image in it. Okay. And this is how it goes into AutoGluon. And so what you want to do is you want to, predict the time to adoption. Now you might say, well, okay, Amazon doesn't deal in cats. Well, we sell razor blades. Now those razor blades have, a title, so that's text. They have some numerical score. They have some more numbers, like how much does it actually cost. So this is a fairly popular razor blade. It's also fairly expensive. There's not just one image, but in this case, well, there are basically 6 or 7 images. And mind you, there's another textual description. And by the way, this isn't an outlier. And by the way, if you were to look at the reviews, there would be probably plenty of pictures of men smiling happily with a shaved face, or maybe occasionally complaining that they cut their nose bloody because they didn't know how to shave. But basically, there are lots of photos for that. And if you want to do any estimation on data like that in Amazon, well, then maybe you need a multimodal tool. Okay. So you might ask, what might you want to estimate? Well, here's one. You might want to answer the question, well, is this the same so far? Right? And I think we can all safely say, well, it is. And again, here you have title and text and some color and a price and some images and some more features. Or, this is clearly not the same product, right? That's some red t-shirt and then a sofa. And yeah, I guess, again, we have all those things. And it helps to know that, you have all those attributes if you want to answer, is a t-shirt a sofa? Right. I mean, yes, okay, a 2-year-old should be able to handle that, but handling it at Amazon scale, you need a machine. I don't think we do perfectly, but at least we're getting less awful at it. So real data is quite messy because you have a lot of different data types. Some of them are, very domain specific. You want to combine all this data. And if you have prior knowledge, well, you should probably use that. Right? And prior knowledge may happen, for instance, by saying, hey, I trained a foundation model, and by the way, I spent $1 million on training it, so it better be good for something. Because my boss told me that since everybody's training foundation models, we need one too, so we trained one. Okay. Now, on to the question as to, how should, the records look like? This would be a typical example of the records, right? So images have, a file name in there, and then there's raw text, and there's a label. And in this case, specifically, you want to find out, how expensive would this house sell for? Okay. Okay, no new questions so far. Oh, I actually never answered Mikola's question. It's great that with AutoML, much more people can easily jump into the field, but it will lead to a situation when there are too many people who can copy paste 3 lines of code but do not really understand how everything works. Absolutely. And I would ask, how many of us in the audience really know in detail how their car works? And I'm reasonably confident that most of us would not be able to draw a working diagram of a combustion engine or discuss the charging circuitry of their electric vehicle. And then when something goes wrong, well, okay, you take it to a mechanic. So I think there's still a lot of need for people who, know machine learning in depth, because if something goes wrong, you need to go to the mechanic. But there are also plenty of cases where you want to put this power into the hands of people who just need a job quickly solved, right? So if I need to do object detection in images, I can tell the person who wants to do that, well, spend the next 2 years on getting a PhD. Or I tell them, well, here's a tool and I think it should work. And if not, then talk to somebody with a PhD. And I can imagine hundreds of cases right now in Ukraine where time is at the essence and where you don't have a time to get a PhD before you use that tool, right? This is exactly why I think that, it really helps. Now, to find the first job in the machine learning field in broad sense, then what solid knowledge should you have? Well, data processing definitely matters. I mean, we can go more into this. So Bodan asked that question. Sorry, Alexandra asked that question. I'll cover more of that later. But what I think is becoming increasingly important is the ability to understand which problems you solve, to ask the right statistical questions, but then also, to know when you can use an automatic tool, right? So we used to teach a lot about, code optimization, and by now, a lot of things happen automatically in your compiler, and nobody's particularly fussed about not being, a real engineer, because you can't really do extensive loop unrolling manually anymore, because we just assume that our compiler does it. Okay. So anyway, let's go to, the the model fusion and, the multimodal models. So there are really 2 things that you may end up doing. One is you just want to, fuse the models where, you go and, fine tune in some reasonable way. So you take a couple of models from, let's say, Hugging Face or whatever, and you fine tune them a little bit. But then what you might want to do is you might want to combine them with CatBoost like GBM and XGBoost and other things and ensemble further. And in that case, well, okay, I cheated. You need 4 lines of code here, but that's really the only difference, right? Because it didn't fit into 3 lines. And you basically, give it the information that, it should use various multimodal models, and then, combine them appropriately. And we'll unpack this in a lot more detail, but basically one just more or less does fine-tuning fancily, the other one combines with CatBoost, XGBM, and others, right? And there are good reasons why you might want to use one or the other. For instance, how many GPUs you have available, how your CPU allocation looks like, and all of that. And so for that, let's start with something called foundation models, right? And I guess everybody knows the reference here to Asimov. So what's out there? Well, there are a lot of models out there, for instance, for text, where you pre-train on a large corpus. For instance, you can predict the next word, you can predict the missing word, you can try to generate an entire sequence of words, and there are new models every day, probably every minute by now. Likewise, for images, you can do, self or unsupervised settings. So if you look at, for instance, the Lion 5B dataset, that's 5 billion images right there. And if you've looked at Stable Diffusion, for instance, so they got a lot of play recently. They trained on maybe about 1 billion of those images to build their good image generation model. And by now there are also a couple of image and text papers. So I just heard about Blip. Albef is aligned before Fusion. Vision Language Transformer Clip is one of the earlier ones. So there are basically plenty of suitably trained and tweaked models available. And with plenty, I mean plenty. So if you look on Hugging Face, and this is from about 2 weeks ago, there were over 60,000 models on Hugging Face available, and over 600 on Tim. And now that Hugging Face hired Ross Reitman, well, you can see those two things fusing very quickly. And so that then begs the question, well, if there are over 60,000 models available, which one should you use, right? I mean, even for vision, right, where it's a quote small problem because it's only 600 models. Well, are you really going to train and compare and test out which one you should pick? Well, maybe, or maybe you leave some of this to an AutoML system to help you combine those things. And by the way, the goal isn't just to how do we use those foundation models, but how do we combine them with tabular models? And right now, there are plenty of teams inside Amazon, but also overall in industry, that experiment exactly with that. And so the first thing that we decided to do in order to make some progress is, well, we created some benchmarks. So we grabbed data sets, a lot of them from Kaggle, and we basically took, tabular and text features and other things and, different metrics, tasks, from classification to regression. And then, so because unless you do that, well, you don't even know whether you're making any progress, right? And there are similar data sets, with images included. But just to give you an idea of things that you could do. You could just turn everything into text and then just throw a transformer at it. And people have argued that, and they've shown that it's not too awful, but I still would say it's pretty awful. Or you can, if you have multiple pieces of text, well, you just take those pieces of text, you add a separator to them, and you just throw it entirely at a transformer. But even then, which of the transformers should you pick? And turns out that, taking, different transformers using different types of training and weighting and averaging over them, all of that helps. It doesn't help like in a spectacular manner, but it helps a little bit. And so what we did in AutoGluon is we looked at those various tricks and then we just, it's a little bit here, a little bit there, and very quickly 100 of those little bits add up, right? Or even further for Fusion. So let's say I have, text and I have maybe categories and I have numbers. I can, map them all through their own deep network. And in the end, I just aggregate things. Or maybe I go and, throw them all through, my embedding. And then I just have a transformer operate on them. Or, anything in between, maybe, concatenate both things individually, have them both output separate outputs. All of those things are possible, and you got to try them out. So this is one of the things that we found kind of reasonably well working. You basically process them appropriately, you concatenate them, you throw them through a tabular network, you get weighting, or you can do this maybe multiple times. And so this gives you a reasonably complex, well, a little bit Frankenstein monster that might combine cat boost with transformers, with maybe a convnet for images, because maybe you need something really quick. and output a category, right? But then, even if we just take, just an ImageNet, just a transformer just for text, if you don't have so much data, well, you then still need to worry about, how do you fine-tune things? Because, you might not take your foundation model just off the shelf. Well, what you can do is you can use different learning rates. And this is actually a good way of, answering the question, should you fine-tune only the last layer or only the first layer or all the layers of your transformer? Well, what you do is you use different learning rates for different layers. And so you're effectively fine-tuning different layers to different extents. This, by the way, is a really useful trick. You should just copy it and adopt it throughout. The last thing is, well, is a single model best? No, again, same thing as before with multiple models. Also, multiple versions of the same model with multiple weights are better. And so you can either just take a uniform average, or you can take some greedy average, and the greedy average performs slightly better. And this is basically model soup or swag. Okay. So all those things combined are what goes into, a multimodal model. Okay. So let's actually use that for, finding a home for a darling. Yeah. What happens is, so we take all the data, and text goes through Hugging Face. Text and images jointly go through some clip. Then maybe the image on its own. We pull a model from Tim. We maybe take a tabular transformer on the tabular data. And then you fuse this all together, and yeah, it works. And yes, Bodan is spot on. Well, we basically look at many different heuristics. And in some cases, we can maybe turn them into a more grand theory. And then when you write it up, you write it up as, hey, I've discovered a great insight and a great theory. But basically, some of the tricks are, how do you modify the parameters and modify only a small amount of parameters while still being able to change a lot? And then, yeah, you wrap it into a pipeline. Yes. And this is actually awesome, because if you think you can improve it, send us a pull request. We'll happily take it. Right? It just has to work better than before. So does it work? Yeah, so for instance, here's, and I apologize for, throwing so many numbers at you, but basically, different versions of ensembles and so on. Well, we compare all those different heuristics, and in the end, well, we pick the one that works best. Is there a way to see what kind of data contributed the most to the prediction, or is it possible to run something like Shapley values? Yes, Shapley values can be run. Unfortunately, if you have multimodal data and you want to run SHAP, it gets kind of expensive. It's on our to-do list. So at the end of the slides, you'll see this as being, part of the wish list of something that we really need. We just don't have enough people to do it. So Vit, if you want to do it, I would be super excited if you could help us, right? Okay, so now let's get to the point of, as everybody already remarked, well, you're building monsters, right? And it's expensive. So, well, what does one do nowadays is distillation. And so to just, drive home the point a little bit, and this is taken from the Megatron paper, and by now, well, these numbers are bigger still, because somebody at the Chinese Academy of Sciences needed to, I think, exceed 2 trillion parameters, because, well, bigger is bigger. Okay, but let me just put this a little bit into perspective. So let's look at, the memory that, different GPUs have. So if you take like an NVIDIA RTX 3080, it has 12 gigabytes, and that will handle around, 5 billion parameter models. A 3090 Ti, well, you can go to maybe 10, 11 billion parameters, but you need a little bit of extra memory. And an A100, okay, so 30 to 40 billion parameters are probably quite doable. Right, this is using bfloat 16 rather than FP32. And if not everything is in bfloat 16, then, those numbers change a little bit, maybe 1 billion up or down. But by and large, this gives you an idea of stuff that, well, at least the first two lines are stuff that most people at a stretch can afford, at least can afford for work, because by now an RTX 3090 Ti costs like $1,200-$1,300 after the prices have come down. So you can get a computer like this probably, and a 3080 is under $1,000 quite solidly. So if you want to put the power of machine learning into the hands of like regular humans who cannot afford, millions of dollars of compute, well, you got to distill. So the basic problem is really foundation models are really too big and too slow, and the models use too many submodels, trees, forests, and whatever. And so the idea is, well, let's go and distill it down to a simpler problem. And by the way, we've done this also for, complex multimodal, complex models with many different components, and distilled into a specific architecture. So you can distill into a neural network, but you could also distill into a decision tree, just because, well, why not? I would not recommend it for text or images because the function class isn't so well suited to it, but you can use this. And there are separate papers that we wrote, and I can maybe go through that afterwards in the questions. But one of the problems is that, so for instance, in distillation, so what do you do? Well, the teacher describes, some function f, for instance, activation of text. The student uses those simpler function to approximate it, and then you train on lots of data to match student to teacher. But, the basic techniques don't necessarily work so well. So the thing is, basically, you want to go and, compress it appropriately. You want to expand the domain. You want to tweak your loss functions. You want to tweak, how you quantize. There's a lot of different tricks that you want to use. And so basically, in the end, you have all those different heuristics. And which one should you pick? So here's our distiller. We basically go and augment the data set. And I'll talk a little bit about the augmentation in a moment. And again, there's a bunch of heuristics. And as I think, as Boran mentioned, well, so we discovered many heuristics and wrapped them into one pipeline. That's exactly what we did. So we have the teacher outputs some objective. We then compare those. So let's actually unpack the loss function that's at the bottom. So we have a distribution over x hat and y hat, so covariates and targets, if you will, drawn from some augmenter on the original data. So for instance, if the original is a cat, then the augmented images of the cat might be cats that look distorted, discolored, cropped, and whatever. No real cats were harmed in the process, but anyway. Then you take a distribution of the actual data from whatever data set you get, and so now you have a couple of losses. And so one is basically you compare the intermediate activations, you look at the predictions for teacher and student, you look at the loss on the augmented data, and then you separately want to make sure that the predictions are accurate on x and y and on x hat and y pairs. So basically you want to make sure that on training data and augmented training data, the student still does well. Why did we pick this? Why did we pick 5 terms? Well, because we couldn't think of a 6th and a 7th and an 8th term. So if somebody has a suggestion of other terms to add, we probably would. Right. And again, this is, exactly, what Bodan said. Well, just throw stuff at the wall. But it's effective if you're patient. So here's an example. So the heart is willing, but the flesh is weak. So you can go and you use contextual augmentation. Let's say you remove the heart, but then, BERT gives you a good idea of which other words might fit in, and you do that. You can do random augmentation. So the text now sounds a little bit more like the way Yoda would speak, at least Yoda in English. I don't know how Yoda in Ukrainian sounds, but in English, Yoda cobbles up word order. You could also translate things and then back translate. And so you get much better paraphrases. And in some cases, you get really fun paraphrases. If you translate the heart is willing, but the flesh is weak, translate it into Chinese and then back, then you get overwhelmed and underpowered. And then for images, but it turns out also for text, you can just combine things. So for instance, you have two images, you take convex combinations of them, and this is called mix-up. Turns out you can do this even for text by just concatenating it. It also works. You can actually verify that humans are pretty good at that too. So next time you're outside a department store and you see things behind the shopping window, and then you see things reflected off the glass, and you ask somebody, what are you seeing? They will be very well able to tell you what's behind the glass and in front and behind them in the reflection. And basically Mixup does the very same thing to make sure that computer vision models also are capable of handling it, and that improves accuracy. Right? Is this terribly deep science? No, but it works. And if you can come up with a fifth and a sixth data augmentation strategy, we probably want to hear from you about it. So Bodan's asking really good questions. Many thanks. Are we speaking of distillation of a single model or distilling the whole pipeline? You can do both. So we have a NURBS paper on distilling the entire pipeline. In this specific case, what I'm discussing is distilling a single model. So you can do either one. Anyway, so for instance, what to use as an intermediate loss? Well, you can use cross entropy, mutual information, mean squared error. You can use Earth mover's distance, right? So, and again, this is stuff that you need to try out. Once you know, you pick one, right? Again, this is throwing many spaghetti at the wall, seeing what sticks and what works best. And there's some patterns that, emerge. For instance, well, big surprise here, right? Augmentation really helps for a small data set and student, right? Which makes a lot of sense, because if you need to do function approximation and the domain on which you're approximating is small, making domains larger helps. Then, various types of mutual information help best if student and teacher are very different. Well, that's also not very surprising, because activations don't mean much if one talks transformer and the other one talks convnet or whatever, right? Or basically, if just the structures are very different, right? Again, it makes sense, because in that case, information theory is about the only language that you can, translate both things into, and it works well. Now, the other thing is, and this is probably something that's quite surprising and new, namely, not screwing up distillation makes a huge difference for the overall accuracy of your model. And yeah, again, this is why we do that. Now, given that distillation kind of matters, you might ask yourself, how do you actually do this? Well, so the first thing we looked at, something called a distillation ratio. And that basically just means of, how much worse is the distilled model relative to the fine-tuned model compared to the fine-tuned the teacher fine-tuned model to the student fine-tuned model, right? Because teacher minus student fine-tuned, well, that's basically the default that you get. And if SDistill is as good as teacher fine-tuned, then you know that your auto distiller actually did a really good job, right? And so what you throw into the auto distiller, basically you want to estimate this function. Well, you want to know the context, task description, just baseline, how, well this overall works, teacher score, number of observations, and then you go and just, learn a cost function. And big surprise there again, if you train your cost function model on more data, well, that helps. And if you then deploy that, automatic distillation works a lot better than, let's just say, not using that, right? And so higher is better. You basically want to be close to 1. Why might you at some point exceed 1? Well, because sometimes maybe the distill model is actually better than the teacher. Here's some more. This is basically just this table, the features for the auto distiller, listed here, and you can see that tasks and context really matter. And now, since nobody within their right mind can remember all the tricks, we wrapped it again into 3-4 lines of code. So you basically load the teacher model, you get the labels, and then you just tell it to fit by using distillation. That's it. Now, fine-tuning a little bit more details there. What can you do? And there's a lot of interesting work that's going on right now. So the goal in fine-tuning is basically, if I have my giant model, let's say a couple of billion parameters, how can I train this and tweak it on a small amount of compute? And so here's, for instance, a model. So I have basically X, then I have, some giant matrix, and that produces Y. How can I actually modify this in such a way as to make it computationally efficient? Because if I only have my RTX 3090 under my desk, then I cannot train, a 100 billion parameter model or even a 2 billion parameter model, but maybe I can tweak it. And so one way that people figured out how to tweak it is to say, well, I just take the output and then I add a little bit to it depending on the input, right? So basically on that output, sorry. So you basically just add a low rank matrix, so down and up, and a ReLU in between, just because nonlinearities are a good thing. Otherwise, it's just a simple projection matrix multiply, and you add that to the output. Okay, that's the adaptive fine-tuning. You can do the same thing where you don't use the output as the input to this thing, but you use the input. And then you don't just add, but you also use gating because, well, why not? Or you can use LoRa, in which case you drop the softmax and you just scale things, and you drop the gating as well. So LoRa is low rank, not the long range, low power transmission. Whoever picked that name, well, I guess thought they were doing something cute, but it doesn't help the citations. Or you can, use a ReLU and drop the scaling and do this. So basically, there are lots of different minor modifications. And again, and by the way, you can now combine this with scaling because, well, why not? But basically, there are lots of minor tweaks. Each of those tweaks is a separate paper, right? And I just summarized 5 papers, at least, in one slide, which tells you that maybe the intellectual challenge in each of those steps is maybe not quite as huge. But then this gives you some improvement, right? And so if you want to do well with fine-tuning, you got to try them all out, find out which one actually works. And we found that LoRa bias is a pretty good strategy. So low rank plus, constant offset. And again, the configuration is fairly simple. You just, run fit with training data and then the hyperparameters for, bias and all of that, and, which strategy to use in this case, LoRa bias. And with that, with basically, fine tuning on, less than 0.5% of the network, you get performance comparable to full fine tuning. If the data set is small, and I know this was really fast, that's why I would like to point you to a lot more examples and tutorials on the AutoGluon website. Okay, so now is a good time if you have more questions before we change gears a little bit, because I want to very, very briefly cover time series, and then we can wrap it up. Any questions so far? And I know this was kind of fast and we went rather deep into technical details. Don't worry, we'll pop back up a few levels. Okay. Don't feel shy. Feel free to ask questions. Okay. Time series. So this is a new thing, and it's still, I would say, work in progress, in the sense that, well, right now, we don't win all the benchmarks yet. We don't even win the benchmarks relative to the precursor of the library. We do well, but we're not the best. And that means we're not done yet. So let's say you have time series for multiple items. So that's panel data. You might want to predict a certain number of steps into the future. You might want to forecast like a target variable, and you have some additional covariates. Let's say you want to forecast, the rain, but you have as additional covariates, for instance, the temperature. Or maybe you want to forecast at regular intervals, how often does my cat meow per hour, right? So that's the kind of problems that we look at. One thing that you can get by now is not just point predictions, but quantile predictions. So that means you get an estimate of, for instance, if you're trying to find out what's going on with COVID, how many people will get sick, and, some range, that, let's say 10 to 90% quantile is within a certain scale. For general regression, I think we do really well on that now. For time series, the accuracy of our quantile ranges is okay, but not great yet. But, you can do that. Part of the problem why time series are weird and different and special is because, you have that dependence of random variables. Because what happens is that you cannot just treat individual observations in a sequence as independent, because they depend on what happened before and what happened the next day. So if I ask you, what's the temperature like in Ukraine on any random day, well, the first thing you're probably gonna say is, well, do you want to know in spring or summer or winter, because that actually matters. And yeah, so that's basically why if I tell you, well, yesterday it was 20 degrees, well, that gives you a good idea that maybe today it's going to be somewhat related, rather than maybe minus 20 degrees Celsius. In any case, so you get those scores. They don't generalize as well as ID data. You need to test things. These are all the challenges that you need to address. And that's basically why time series took us a little bit longer, and why, in general, if you want to do time series estimation, you have to be prepared that maybe the accuracies it takes longer to get high accuracy there. So what do we have by now? Well, the API basically looks the same as the AutoGluon API, so that's a good thing. We've started again by taking a zoo approach by grabbing a whole bunch of different, time series models, most notably Gluon TS, but then also Profit and SK Time. And, within SK Time, there's a bunch of models on their own. And then to wrap this all into AutoGluon time series. And if you want to help, we could probably use some help. Now, things that you may want to do there, well, you want to get, just sequence forecast, but maybe you want to get entire quantiles. And so some of the models that we offer by now is, deep AR. There are different, quantile CNNs and RNNs, simple feed forward networks, Facebook's Profit, and then SK Time has a couple of things. All of this goes into the mix. And unfortunately, a lot of the reasoning about stacking and so on and bagging doesn't work so well because you have dependent random variables. So this is still something that's a little bit in flux. Anyway, we do ensemble. There is an HPO problem that's probably a lot more pertinent there just because, well, yeah, just averaging over models isn't quite so effective. It depends on if you have dependent random variables. You can't just say what's the average of tomorrow's temperature if one model predicts that today is 20 degrees and the other one predicts that it's 5 degrees, right? So that entire part already gets messed up. So what I'm mostly telling you is, yeah, stuff is there. It's probably better than what you would find off the shelf elsewhere, but there's still a very long way to go. And some of it are research questions. So this gets me to the part where I need your help. And so what do I mean by I need your help? Well, here are some of the things that we want to add. And this slide is by now maybe a month or two old, and you can see that some of the things by now have already started happening. But basically, better data ingest. So what was asked before, what's the format of the CSV file? Well, we're pretty robust to that and other files. So for instance, if pandas can take it, we probably can deal with it too. Also because we use pandas. Right now, we don't have a modeling GUI. If somebody wants to do that, it would be great. Visualization, yes, Shapley values are good, but maybe you also want to have GradCam and similar things for vision models. Much better automatic problem detection. I think we're pretty decent, but you can always get better. Multimodal, I mean, you saw that this is very active research right now. I would like us to be able to go up to essentially 10 to 20 billion parameters on a single GPU. Like there are some issues in terms of, storing intermediate gradients and all of that. And much better models for integration with labeling problems, because in many cases when somebody has machine learning problem, they have some data, but then they train a model and they go like, well, that works okay, but I need to learn more things. So for instance, if I have a computer vision problem and I want to detect unusual objects that I usually don't see because maybe some new objects appeared, let's say somebody is flying UFOs, I want to have a UFO detector, so I need to label it and I need to get that UFO detector working very, very quickly. So that integration needs to work. Fairness, there's some work going on. Problem with fairness is that sometimes it can do way more harm than any good. Explainability, causality. I think Bodan's been asking a lot of questions about that. Yes, we want it. We always want to go faster, cover more hardware. The last thing is, I mean, ultimately what people would want is just, okay, here's an endpoint, just throw data at it and magic happens. And I'll go into this in a bit more detail in a moment, but I quickly want to answer Bodan's question, which tasks could eventually be automated by AutoML and which be left to people and developers? Well, here's the thing. Anything that I can solve through research, where I want to solve a problem, ideally I want to solve this problem once, and I want to solve it well once, and then rather than having to teach everybody how to repeat the steps that I just did, I want to make this solution available to everybody else who also wants to use it. And that's really the same as, let's say, with, software libraries. So if somebody implements a good PDF to SVG converter, then, I want to put this up on Mac ports or Ubuntu or whatever, or Conda, and then everybody can install it, or NPM, or whatever package manager you're using. But basically, at that point, once somebody has solved the problem, you want to make that functionality available to everybody, rather than forcing everybody to read your paper, re-understand it, re-implement it, and redo it. Such that, as a scientist, you can focus on the more interesting problems, namely the ones that nobody else has asked yet. So basically, I want to automate all the tasks that are boring and can be automated. And I don't know how far we can push it, but we'll surely try to push as far as we can. There are some cases where this can do a lot of harm, namely in the case of fairness. And if there's some time, we can maybe cover it later. But let's just look at data ingest. There's like a crazy amount of really boring stuff. So, does my data sit locally or does it sit in the cloud? And then which format does it sit? Can I read in S3 format from that? Do I need a database adapter? Which of the 20 databases that are out there that speak their own language is it? I mean, even if you look at Amazon, we offer on AWS, I think, 10 different databases. Well, why do we do that? Because customers have very different needs. If you need to ingest the data from all of them, somebody needs to write those adapters. Then there are data lakes, and maybe in the data lake, you don't even quite know yet what the schema was, because why not, right? Then maybe you don't want to have to manually rerun the pipeline whenever data changes. You want to have maybe an update trigger. Maybe you want to combine this with feature stores because your predictions go into the next line, right? So this is really just data ingest. And even that, I mean, if somebody wants to help us, I mean, we'd be very, very grateful. This is a lot of work, and it's impossible for my team to do that on their own. Also, because everybody has their own needs there. Then in modeling, well, yes, drag and drop model combination and tools. I think there's a lot of cool things going to happen. I think PyScript will make a huge difference there. Also visualizing inputs better. So similar to what Joe Hellerstein and others with Trifactor did. This is very nice. Also detecting anomalies. So now you might say, well, this needs a separate anomaly detection implementation. Yes. By the way, what's an anomaly? Is it rare data? Is it data I've never seen? So that is its own kind of worms. Also detecting label leakage. And by the way, this is a real problem. So you might think that, everybody working in a big company is smart. Well, maybe smart, yes, but they're still humans and they still make mistakes. So a friend of mine made the following mistake. So he used Autoglue and, it worked well. And then some other team came along and they said, we have those better embeddings. Why don't you use them? And he used them and the accuracy was amazing. And then in the end, somebody on my team, went to debug this a little bit and found out that by mistake, he had trained on the labels. Well, not explicitly, but the labels were encoded in some text field in some way. And that's why he got this really good accuracy. Well, is it stupid? Yes. But does it happen even to senior people? Yes, it does. When you're in a hurry, you make mistakes. but this is, boring stuff that you want to automate out, because, I mean, this is a very unglamorous job, right? Then would you like to have better ways of tracking performance, right? Much better debugging queues, of course you do. In terms of problem types, well, we cover a lot. I mean, we have some segmentation detection. I think even some OCR applications by now added, but basically there's a lot of stuff that, okay, I apologize. Sorry. Sorry, our corporate meeting system was reminding me of a meeting that's actually not happening. But basically all those things, are being added. Now, the other thing that you want is, for instance, much better automatic calibration. So there's a really cool thing going on right now that goes under the moniker of conformal methods. So that basically means, if you say, well, my system is 95% certain, then, it is. I mean, anybody who knows conformal knows that what I just said is horribly wrong. I'm just oversimplifying such that I can quickly explain it. But essentially getting some idea of the accuracy of the model would be really good. Much better integration with labeler tools and annotators, building an active learning system that works. So I can imagine many, many cases, especially if you needed to build some computer vision models for new applications very, very quickly. I could see this being super useful. Weak supervision. For instance, if I know, well, okay, here's a collection of images and they contain 5% cats, build me a classifier that actually detects at least 5%. Model updates in a way that is computational efficient. Then, foundation models. There's still a lot to be done. Yeah, so this is really all of machine learning eventually. So TLDR, so our plan is really to do more of everything, and we'll to some extent go in the direction that everybody needs. Now, I'm just the guy who does the talking. This is the team that does the actual work, and there are really three people that stand out there. That's Nick, Xingjian, and Alex. And maybe if you reach out to Alex Shirkov, he'll be happy to, present some more and go into some more technical detail. So he's actually from Ukraine. Yeah, so just reach out to him and he can probably give you a much more hands-on view. And with that, I really want to thank you for your time. So this is the work of a lot of people. I'm just the guy who's doing the presentation today. And it's an open source project, all under Apache. If you want to help, we'd be delighted to get you help. Okay, and if I can help in some other way, also let me know. Okay, that I think is the end of the main presentation. I don't know how you want to do the questions now, maybe through Slido. Either way is fine.
Yeah, I think we have a couple of questions left. So how do you see the distribution between deeply knowledgeable people, mechanics, versus AutoML adopters in the future?
I don't think it's binary. Quite the opposite. I think there is a transition, and sometimes you start by using AutoML tools, and then you start modifying them. You basically can go and I mean, this is one of the main tenets: batteries included but removable. So you can customize which embeddings. You can maybe include your pre-trained embeddings. You can add your own models. You can improve the aggregation strategies. So there is so much you can do once you look under the hood. This is more just a matter of really lowering the bar of entry to make it easy for people to really learn about machine learning before and to use it before having to get a PhD, because sometimes you just need a problem solved, right? Likewise, if you write a piece of C code and you compile it, well, you just need that done. You don't need to take a class in compilers. Yes, okay, if you take a class in compilers, you can probably do a much better job, and you will be able to set the flags of GCC properly, and you know what to unroll and what not. But most of us just want to get the job done. Right? So that's why.
And I think that one of the last questions, so is there a way to see what kind of data contributed the most in the prediction? Or is it possible to run something Shapley feature importance on top of it?
Yes. So there is a notebook that describes how to use SHAP. So basically get Shapley values. And that works quite reasonably well for tabular. For multimodal, I don't think anybody actually has written a paper on interpretability for multimodal. So maybe if there are any PhD students or master students or whatever on this call, I mean, you should probably write that paper. It's still 1 month until iClear time. You can probably pull that off. Because then you're the first one and people will cite you for it. Let me know if you do and send me a copy. The point being, we just haven't done it yet because we don't have enough time. I think there are tons of good ideas out there on how to deal with interpretability. If you want to know a little bit more, so in the Stanford class that I taught basically earlier this year, there's a bit of detail. Actually it was late last year anyway. But there's one lecture on just interpretability and explainability and how the various criteria can be used. A lot of it is hand wavy. It's also because causality is hard, and it's very easy to get it wrong. There's a separate library called PyY. That's from my causality team in Tübingen. Well, they actually contributed to PyY. So it used to be called DoY, and we talked to Microsoft and went like, hey, we have some code, and can we maybe put it into a separate org? And so this has become PyY, and by now it's about half the codes from the causality team in Tübingen uses Granger causality. So that's for really sophisticated data analysis. For that, you definitely need still a reasonably advanced degree in machine learning to use it.
And I think the last question is about running pipeline in parallel. So does AutoGlan support pipeline parallelism?
Okay, and so let me actually unpack this in 2-3 different ways, because I think the specific question is about training large deep learning models and using pipeline parallelism there. And right now, we don't support that just yet in AutoGluon, because that's more something that your deep learning framework would do. And however, if you need, parallel distributed model building, by now with Ray, you can do that quite nicely in AutoGluon. But it's just that AutoGluon is right now not a one-stop foundation model training tool, right? So for that, I mean, look at DeepSpeed, look at FSDP. I don't know whether PaLM Pathways, so whether Pathways by now is released from Google, but their paper is fairly well written, so this is a good place to start reading. All of those things will get you somewhere. Maybe at some point in the future, AutoGluon will cover foundation model training as well, but that would be a significant capability extension, and it might be a separate library because it's quite different.
Okay,
So,
I think it was
go ahead.
the last question. Thank you, Alex, a lot for your presentation today and for supporting AI for Ukraine project. I hope everybody enjoyed as well as I did. Actually, thank you all for all your questions. I think with that, we are closing this session. Next week, we're going to have tutorial with Sergey Matusevich, principal data scientist and applied data scientist at Microsoft. So he will share his knowledge and expertise in model compression for deep learning. So again, thank you all for attending, and see you next week. Yeah, and stay tuned about next sessions. And if you still have a minute, we would love to hear from you. How do you like the session today?